we have seen the ideal characteristics of operational amplifier. Okay, so we have seen the ideal characteristics. Okay, so in the ideal characteristics we have seen that the CMRR it is infinite. Okay, so what is common mode rejection ratio? CMRR stands for common mode rejection ratio. So in short, it is also written as CMRR. So it is equal to AD by ACM. What is AD? AD is differential voltage gain. And what is ACM? ACM is common mode voltage gain. Okay, so from this relation it appears that CMRR it is equal to AD by ACM, and normally this AD is differential voltage gain, which is nothing but the open loop gain. Okay, so AD is what? AD, its normal range is 10 to the power 5. Okay, and ACM is, it is very small. In ideal case it is equal to 0. Okay, so common mode rejection ratio in ideal case it is infinite. Okay, so how we can calculate both these, AD and ACM? This is RL and V output. Suppose this is V in 1 and say this is V in 2. Okay, and this is VID. Suppose this is point A and this is point B. Okay, so VID is what? VID it is equal to VB minus VA. Okay, so how we can determine AD? AD it is equal to V output divided by VID, which is equal to V output divided by VB minus VA, like this. So in this way we can determine AD. Okay, so AD it is equal to V output divided by VID. Okay, now this is differential voltage gain. Then how we can calculate common mode voltage gain? This is RL, V output. So from this circuit we can determine the common mode voltage gain. So in order to determine common mode voltage gain, we have to give the input to both inverting and non-inverting terminal from the same source. Okay, so it will be connected to both. So from this we can get ACM. Okay, normally ACM is very less. In ideal case it is equal to 0. So in ideal case CMRR it is equal to infinite. This is in ideal case. Okay. So in this way we can determine the common mode rejection ratio. So in case of operational amplifier, for ideal case CMRR it is equal to infinite. Okay. So it rejects the common mode signal. Okay. So higher will be the common mode rejection ratio, better will be the operational amplifier, as it rejects the common mode signals. In any amplifier, okay, if noise is present, okay, so noise will be present at both the input, and the magnitude of the noise, it will be same for inverting input and for non-inverting input. So noise may be considered as common mode signal. Okay. So if the noise is common mode signal, so higher will be the common mode rejection ratio, it will reject the common mode, so it will reject the noise signal. So higher will be the CMRR, better will be its rejection ratio of noise. So noise will be rejected if CMRR of operational amplifier is higher. Okay. So we are choosing higher value of CMRR in an operational amplifier to reject the common mode signal, that is to reject the noise. So magnitude of noise at this terminal and at this input terminal both are same, so both will be considered as common mode signal. Okay. So for a common mode signal and for higher value of CMRR, it will reject the common mode signal, that is it will reject the noise. So this is the significance of CMRR in operational amplifier. Then we will study about slew rate. So what is slew rate in operational amplifier? It is dV0 by dt, maximum value of dV0 by dt, it is equal to slew rate, and it is expressed in volt per microsecond. Its unit, it is generally expressed in volt per microsecond. Okay. So if V0, it is equal to Vm sin omega t, where Vm is the peak amplitude of the signal. Okay. So how we can represent V0? Suppose like this. This is Vm and this is minus Vm. Okay. So Vm sin omega t. Okay. Now dV0 by dt, dV0 by dt, it is equal to Vm omega cos omega t. Then from this we can determine dV0 by dt max, it is equal to Vm into omega. So from this we can determine the slew rate. So slew rate, it is equal to Vm multiplied with 2 pi f. Okay. So from this we can determine f maximum. This is maximum value. So it is f maximum, it is equal to slew rate divided by Vm into 2 pi. So from this expression we can determine the maximum operating frequency of operational amplifier. So if the frequency of the signal is more than f max, then the output will be distorted. So f max, it is equal to slew rate divided by Vm into 2 pi. So from this we can get the maximum operating frequency in case of operational amplifier. Okay. So if the applied frequency, that is if the input frequency of the signal is more than the f max, then the output it may be distorted. Okay, so we have to give the input signal such that the frequency of the input signal should be less than f max. Okay, so this is the significance of slew rate in operational amplifier. Then we will study about input offset voltage. Input offset voltage. What is input offset voltage? Okay, so for this we will draw the pin diagram of IC 741, 1, 2, 3 and pin number, this is pin number 4. Similarly, this is pin number 5, 6, 7 and this is 8. Okay, now this is operational amplifier. Okay, output is connected to pin number 6. Okay, and this is minus VEE. Okay, so it is minus VEE, it is connected to pin number 4 and plus VCC. This is VCC, it is connected to pin number 7, it is plus VCC, this is output, this is offset null. Okay, and this is inverting input. This is pin number 3 is non-inverting input. Okay, and pin number 5 again it is offset null. And pin number 8 it is not connected. Okay, so this is the pin diagram of IC 741. IC 741. Okay, now what is input offset voltage? Input offset voltage is the voltage that must be applied between the two input terminals of an operational amplifier to null the output. To null the output means to get V output is equal to 0. Okay, so suppose this is an operational amplifier. If it is connected to ground, then V output in this case it will be equal to 0, but sometimes it is not equal to 0. This is because of input offset voltage. So in IC 741 the maximum value of input offset voltage it is 6 millivolt. Okay, suppose like this. This is ground and this is ground. Okay, and this is V out, and it is connected to VCC and it is connected to minus VEE. So if this is plus 15 volt and it is equal to say minus 15 volt. Okay, now under this case if it is coming as V output it is equal to say 2 millivolt. Okay, so what we will do, we have to connect 2 millivolt, that is input offset voltage, it should be equal to 2 millivolt. So in the input side we have to connect 2 millivolt so that the output V output it is equal to 0. Okay, so this is input offset voltage, that is the input voltage that is given to the input terminals of an operational amplifier to null the output, means to make the output voltage 0 when both the input terminals are, suppose it is ground, then output voltage it should be 0, but it is not 0 because of mismatching. If it is perfect, see we have seen the ideal case of an operational amplifier that is perfectly matched. So if the operational amplifier is perfectly matched, then in that case for this condition V output it will be equal to 0. V output it will be equal to 0 when it is perfectly matched. Okay, so if it is perfectly matched, then V output it is equal to 0. Okay, input. So how V output it is equal to 0? It is done by using offset null. Here we are seeing two pins, pin number 1 and pin number 5. It is used for nulling the output. Okay, so we have to connect register. Okay, like this. This is minus plus. Okay. Okay. So what we have to do? Pin number 1 and pin number 5. This is minus VEE. Suppose this is pin number 1 and pin number 5. Pin number 5. Suppose this is pin number 5. Pin number 1, pin number 5. So we have to connect like this. And what we have to do? We have to connect like this. This is 10 kilo ohm potentiometer. Okay. So this figure is like this. So how we can offset? How we can make the output voltage 0 if this is connected to ground? These two terminals are connected to ground. So we have to connect one potentiometer between terminal 1 or between pin number 1 and pin number 5. Pin number 1 and 5, these pins are offset null. Okay, and we have to vary the wiper. Position of the wiper, it is varied to adjust the output offset voltage. So if output voltage, if it is equal to 0, then we have to fix that the position of the wiper at that position, so as to make the output voltage equal to 0. So in this way we can make V output equal to 0 when these two terminals are connected to ground. Okay, by connecting one potentiometer between pin number 1 and pin number 5 and adjusting the position of the wiper by connecting this VEE like this. Okay, so this is all about input offset voltage. Then we will study about input offset current. So what is input offset current? This is inverting input and this is non-inverting input. Okay, two inputs are there. This is inverting input and this is non-inverting input. And suppose this is RL and this is V out. Okay, say this is IB1 and this is IB2. So input offset current, it is equal to mode of IB2 minus IB1. So what is input offset current? It is the difference of the two input currents. Okay, IB2 and IB1 in an operational amplifier. Okay, so its maximum value of input offset current in IC 741, it is equal to 200 nanoampere. This is maximum value. Maximum value of input offset current in IC 741, it is 200 nanoampere. So how it is calculated? It is equal to mode of IB2, that is the current flowing in the non-inverting terminal minus current flowing in the inverting terminal. Okay, so in this way we can determine the input offset current in an operational amplifier. Then we will study about input bias current. What is input bias current? Okay, so again input bias current, it is equal to, suppose this is IB1 and this is IB2 and this is say RL and V output. Okay, and this is IB1 and this is IB2 and say this is V1 and V2. So IB, it is equal to IB1 plus IB2 divided by 2. So input bias current, it is the average of the two input current, that is IB1 and IB2. So it is non-inverting, it is inverting input and this is non-inverting input. Okay, so IB, it is equal to IB1 plus IB2 divided by 2. It is the average value of the input currents that is flowing to the inverting and non-inverting terminals of an operational amplifier. So its maximum value in IC741, it is 500 nanoampere. It is the maximum range or maximum value of input bias current in IC741. Okay, we will study about open loop, configurations in operational amplifier. Open loop configuration in operational amplifier. Okay, so generally there are three types of configuration. First one is inverting amplifier. Second one is non-inverting amplifier. And third is differential amplifier. First one is inverting amplifier, second one is non-inverting amplifier, and third one is differential amplifier. Okay, so we will study all these three. See, in case of open loop configuration, non-inverting terminal and this is inverting terminal. Okay, and if it is connected to some source, okay, suppose this is V2 and say this is V into and this is say V in 1, this is say V in 1. Okay, and this is VID, it is VA and say this is VB. Okay, now see, suppose the internal gain of the operational amplifier, it is A. Okay, now V output, it is equal to A times VID. Okay, what is VID? VID is equal to VB minus VA. Okay, it is VB minus VA. Okay. Now we have seen the ideal characteristics of an operational amplifier. The internal resistance is infinite, and practically also the input resistance of an operational amplifier, it is very high. Okay. So under that situation, the internal resistance of the voltage source we can neglect. Okay. So VA is equal to V in 1 and VB it is equal to V in 2 if we are ignoring the internal resistance of these two voltage sources in comparison with the very high input resistance of the operational amplifier. Then it is equal to A into V into minus V in 1. Okay. And we are knowing that A, it is approximately, it is in the range of 10 to the power 5. Okay. This value is very high, gain is very high. So even for the small input, suppose VID, if it is very small, then also V output it will go to saturation value. Okay. Even for a small VID, V output it is saturated. Either it may go to plus Vsat or it may go to minus Vsat. So for linear application, okay, suppose we want to draw V output versus VID. So during only small interval, it will be in linear region. After some value, after increase in VID, it will reach to plus Vsat or minus Vsat. Okay. So open loop configuration, it is generally used for generation of square waves. Okay. So we have to see about the three types of configuration in open loop. In case of open loop, the first configuration that we will see is inverting amplifier. This is in open loop configuration. Open loop configuration, the first configuration that we will see is inverting amplifier. Okay. So first of all, we will see the circuit diagram. Okay. So this is the circuit diagram of inverting amplifier in open loop mode or open loop configuration. Okay. So how we can calculate AD? AD it is equal to V output divided by VID. Okay. And how we can calculate V output? V output it is equal to suppose A is the gain of this amplifier. Okay. So how we can calculate V output? V output it is equal to A times VID. Suppose this is VID, A times VID. So it is equal to A into, suppose this is point B and this is point A. So it is VB minus VA. Okay. So it is equal to VB means voltage at point B, it is equal to 0 because it is connected with ground, and VA, it is equal to V in 1. See, if the internal resistance of this voltage source is very less as compared to the very high input resistance, then we can say that the internal resistance can be neglected. Okay, so under that situation, VA, it is equal to V in 1, so it is equal to minus A into V in 1. Okay, so we can write in inverting amplifier, what we can write, V output, it is equal to minus A into V in 1. It is equal to minus A into VA. Okay, why it is equal to V in 1? See, V in 1, it is equal to VA if the resistance of this voltage source is very less as compared to the input resistance of the operational amplifier. In ideal case, the input resistance of the operational amplifier is infinite, okay, and practically it is very high, so we can neglect the input resistance of this voltage source. So V output, it is equal to minus A V in 1, this is V in 1, and it is equal to minus A VA. So this is the expression for V out in case of inverting amplifier. So in case of inverting amplifier, what we are saying, V output, it is equal to minus A into V in 1. Okay, suppose A is 10 to the power 5. Okay, and if V in is say 1 millivolt, V output minus A into V in 1, it is equal to minus 10 to the power 5, so it will V output, it is equal to minus V sat. So generally we are saying that V output for a very small V in, V output, it will always go to minus V sat. Okay, so this is all about inverting amplifier in open loop configuration. In open loop configuration, because of very high gain, this gain, it is in the range of 10 to the power 5. Even for small V in, V output goes in saturation mode, so it reaches to minus V sat. Then second type of configuration we will see is non-inverting operational amplifier. Okay, non-inverting operational amplifier. So the circuit diagram we can see. So this is the circuit diagram for non-inverting operational amplifier in open loop configuration. Okay, so in this case, V output, it is equal to A, where A is the gain of this operational amplifier IC741. So A into VID, this is VID. Suppose this point is A and this point is say B. Okay, so it is equal to VID, it is equal to A into VID. VID is VB minus VA. Okay, so it is equal to A into VB it is equal to V into minus VA, it is equal to 0, as VA it is connected to ground, so it is equal to 0. So it is equal to A into V into. Why it is V into? Because the internal resistance of this voltage source is very less as compared to the very high input resistance of this operational amplifier. So we can neglect the input resistance of the voltage source under this case. Okay, so it is equal to A into V into. So we can write V output, it is equal to A into V into, it is equal to A into VB. Both are same. Now what we can see here, V output it is equal to A into V into. Normally A it is equal to say 10 to the power 5. Again if V into it is equal to 1 millivolt, so it is equal to 10 to the power 5 into 10 to the power minus 3 volt. So it is equal to 10 to the power 2 volt. So but V output it is more than this Vsat. So V output here it is equal to plus Vsat. Okay, so for a very small input voltage, V output goes to plus Vsat in case of non-inverting operational amplifier in open loop configuration. In case of inverting, what we have seen in the first case, in case of inverting operational amplifier, V output goes to minus Vsat for a very small input voltage. And here what we are seeing, in case of non-inverting operational amplifier, for a very small input voltage, it goes to the saturation, means it goes to plus Vsat. Okay, so the output voltage it goes to saturation for a very small input voltage. Okay, so this is all about non-inverting operational amplifier. Then we will see about third one is differential operational amplifier. Again it is in open loop configuration. Suppose this is V in 1 and say this is V in 2. It is connected to plus VCC and it is connected to minus VEE. This is RL and V output is like this. So how we can express V output? V output it is equal to A. A is the gain of this operational amplifier multiplied with VID. So this is A and this point is B. It is VID. So it is equal to A into VB minus VA. Now if the internal resistance of these two voltage sources are very small as compared to the very high input resistance of the operational amplifier, then we can neglect the input resistance of V in 1 and V in 2. So we can also write it is equal to VB, it is equal to V in 2 minus V in 1. So we can write V output like this. V output it is equal to A times V in 2 minus V in 1. So this is the expression for differential operational amplifier. Okay, it is A times V in 2 minus V in 1. So for this differential operational amplifier in open loop, you can write open loop. In open loop configuration, also due to very high value of A, again it goes to V output, it will go to plus minus Vsat for a very small input voltage. Okay, so this is the main disadvantage of open loop configuration. In open loop configuration, we are seeing that the main disadvantage is that V output it goes to plus minus Vsat even for very small input voltage. Okay, so this is the main disadvantage. So the operational amplifier in open loop configuration, it cannot be used for linear application. For linear application, it cannot be used. That is, operational amplifier in open loop, it cannot be used for linear application, because for linear application we have to use this curve only up to this. This is in linear range. This is what? This is VID versus V output, and this is plus Vsat, and this is minus Vsat. Okay. For linear application, we have to use till this one. Okay. But in case of open loop configuration, okay, because of very high, this is very high, A is very high. Because of very high A, V output generally reaches to plus minus Vsat even for a very small input voltage. So this is the major disadvantage in case of open loop configuration. So we are using the operational amplifier in practical circuit by using closed loop configuration. Okay. So in next class we will study about closed loop configuration of operational amplifier. Thank you.